Good evening, people. So, mathematics, yes, is a lot of things, and tonight we are in for a cocktail of mathematics. This, of course, is the kind of battle that you don't want to have your cocktail in, because it's impossible to keep it in the battle. Here, what is mathematics about? First, one has to remember that mathematics is a science, and mathematics, as such, studies the world in which we live. It is about the examination and the understanding of the rules of the world. Just one special thing about mathematics is it never interacts with the world directly. If you are a physicist, you make experiments. If you are a mathematician, you don't make experiments, you just work on the mathematical formulas, which are a reflection of the mathematical reality. There is one poetry which I like to invoke when speaking about nature of mathematics. This is The Lady of Shalott, poem by Alfred Lord Tennyson. This is an illustration about this poem. And in there, the poor lady which is there has been a victim of a curse by some evil magician. It's a legend from the Arthurian times, and she cannot see the real world directly, only through the mirror. This is the mirror. The curse she abides by until one day comes Lancelot du Lac, and then he's so pretty, so handsome, that she looks at him directly, and then the curse is on, she dies. It's tragic, it's very tragic. Yes. And her body drifts through on the waters here. And then many people have wondered if there is a special hidden meaning to this poetry. And because the author did not explain, as usual, we can imagine whatever we like. I like to imagine it's an allegory of the mathematician. When she mixes reality and the reflection, then she dies. She has to only study the reflection, and these are the abstract formulas. So if you're a mathematician, you study the world, but through the formulas. Mathematics is indeed abstract by definition. It may deal with very concrete objects, but through the abstract reflection. For instance, the water here, on which the corpse of the Lady of Shalott is drifting. You can feel it, you can touch it, you can make experiments on it, but you can also try to write the equations of the flow. And this is a mathematical adventure which started in the middle of the 18th century. And this is an abstract equation that can describe any flow, provided it has the right physical characteristics, in this case, incompressibility. Many other examples arise about abstract, interesting phenomena whose study becomes an abstract problem of interest in itself, and which are inspired by reality, and which then can be applied to many, many real problems. If mathematics is often thought to be just abstract with no applications, this is a sure mistake. We'll see examples of applications coming from mathematics, very often not wanted. I mean, not imagined by their authors of the theories. Another misconception about mathematics is that it is all well known. Of course, what we study in high school has been found long time ago. But this is a misconception. And there are many, many open problems which are being solved from time to time. Around the world, each year, there are more than 100,000 new theorems being proven, which is a huge quantity, of course, making it impossible for anybody to know the whole of the discipline, or even a significant portion of it. If you ask a mathematician which is the most important problem that he would like to solve, you will get an answer which may depend from mathematician to mathematician. Some will tell you that this problem is so important, that other problem is so important, and the answer may vary. But if you ask them, which is the most famous mathematical problem, certainly they will answer it's the Riemann hypothesis. Here I put some big words, deeper scientific mystery of our times, but it is really a deep scientific mystery. So who was Riemann? One of the most extraordinary mathematicians of all times, most extraordinary scientists of all times. And his hypothesis, so it's something that people believe to be true, but it's not proven yet, is easy to explain. Okay, don't here there is a bit less contrast than I expected, but never mind. The Riemann hypothesis is about a certain function. A function is like a curve, you know, depending on the parameter. This is a definition of the function of Riemann, called the zeta function. Just, it's a function defined on complex numbers, so you could imagine as a function defined on the plane. Imagine that to each position on the plane, we associate one complex number, so it's like another couple of numbers. And you ask, when is it that this function becomes equal to 0? It's known that it is equal to 0 for when we are at point -2, -4, -6, etc., -8, -10, whatever. But we know there are other points where it becomes zeros. And Riemann conjectured that all these other points are on a single line. All on a line, vertical line. Then you would say, okay, let's compute them and check. But there are infinitely many. Okay, let's compute many of them. As soon as computers were made, even from the 50s, people started to compute the zeros of the Riemann function. And they found that they were all on the same line. And when the computers became more and more powerful, it was checked for more and more zeros. Now it has been checked for thousands of billions of them. And still, it's not proven. Because the mathematicians, they are the extreme guys, you know, the really hardcore guys. Even if we have 1 billion clues, we don't consider it proven. And that's the only field of all of knowledge, of man's knowledge, in which we are so tough. In usual life, if you have a prediction and it's realized 1,000 times, it will be more than enough to accept it as a valid theory. But in mathematics, 1 billion clues is not enough. You want the complete proof, which makes absolutely no chance for error. Now, why do we care about this Riemann hypothesis? Well, for many reasons. In particular, it's related to the distribution of prime numbers. Prime numbers are these elementary numbers like 2, 3, 5, etc., 7, such that every number is a product of these prime numbers in a unique way. These numbers, we know they have many properties, but their distribution, where they pop out and so on, is not fully understood. If the Riemann hypothesis is true, it means that in a certain way, these numbers are randomly distributed from a distance, let's say. A few years ago, a British journal fantasized that if this hypothesis was solved, it could bring disaster for internet. It was one of the prizes put for reward by a math institute for $1 million. And it's very weird. Why would that be a disaster if we know something more? Now, the reasoning you can reconstruct is the following. Because it's related to prime numbers, and prime numbers were extremely useful to code things encryption, security of transactions online and so on was based on prime numbers for a long time. The deduction from the journalist was that if we solve this problem, it will be easy for pirates to crack the codes. Of course, if you understood what I said before, you see that this guy hasn't understood anything. You know, if you want to crack the code, you have to find the product of prime factors. So you have to find the prime numbers behind the key. What good is it to know that the prime numbers are randomly distributed if you want to find them? It's not very useful, you know? Not very useful. But anyway, we don't need this kind of sensationalism. The important about the Riemann hypothesis is that it gives some beautiful insight into the structure of a basic object, the prime numbers. Also, it's related to other fields of science. For instance, there is a very famous connection, very weird, that we don't understand, between the prime of the distribution of prime numbers, statistical distributions of prime numbers, and the statistics of the energy levels of a random atom. It's a connection that was observed and never explained. This shows you the number of consequences that could come from this understanding. Riemann was remarkable not only from this hypothesis, by the way. He also left his mark in geometry. And now we call Riemannian geometry the basic non-Euclidean geometry, which is what happens when you deal with spaces which is not flat, but curved, let's say, distorted. The Earth, for instance, we know is not flat. It was shown long ago. So if you do geometry on the Earth, it cannot be the flat geometry that we learn in school. How do you handle this? Riemann, it was in the middle of the 19th century, showed us how to handle this. In the world of Riemann, units of length may change from place to place. So what has this length here, maybe has that length here, and so on. And you still have a notion of shortest path between one point to another, even though these are not straight lines. For instance, if you want to go up here from the bottom, from down, you will go through something which is not a straight line, but that maybe is the most economic path, the one that consumes the least energy. Similarly, if you fly, I don't know, from Paris to New York, from Copenhagen to New York, if you look on a map, the trajectory of the plane, it will not be like this. It will be something like this. It will be a curved path. How to understand all these curved paths? I mean, in geometry, the lines, we understand them. A line has simple properties and so on, and we study them when we are children. But a path that can be any kind of distorted path, there must be some way to understand them. Mathematics is not just description, it's classifying and understanding. And Riemann and his master Gauss showed us how to classify these shortest paths or geodesic curves, thanks to the notion of curvature. So there is this curvature is something that can be positive or negative or zero. Zero is like flat. And if the curvature is negative, the geodesics will spread apart. They will become more and more distant from each other very fast. What if the curvature is positive? They will not separate so fast. Here is an example of a Riemannian geometry. This one is called the hyperbolic disk, hyperbolic space. It was discovered in the 19th century, beginning. In this artist's view, every fish has the same length. Just the units of length change from place to place. And if you are a fish here, making your way here, the universe appears infinite. You approach and units of length become smaller and smaller and smaller and smaller. And if you draw a triangle in this, using shortest path, here is how the triangle looks like. And if you measure the distance between these 2 points, it becomes extremely large, very, very, very large as time goes. Notice that the sum of the angles of the triangle here is less than 180 degrees. The triangle is said to be skinny. On the contrary, if you draw a triangle, a geodesic triangle on a sphere, the triangle will look fat. And see what I was saying. This is positive curvature, this is negative curvature. Positive curvature, it's geodesics, they separate rather slowly. Take these two geodesics. Here they cross, and they will cross again on the opposite point. Have we ever seen in the plane two lines crossing once and then crossing another time? Of course not. If two lines cross once, they will never cross again. But in the world of positive curvature, it's very likely that two lines which cross once will cross a second time. They don't get separated as much as the lines. Notice that the sum of the angles is more than 180 degrees. In fact, this is 3 right angles, so 270 degrees. And when I do this in high school, always I ask the students, try to imagine which is the maximum sum that you can make for a triangle on the sphere. And usually after some time they manage to find that you can go as much as 540 degrees for the sum of the angles of a triangle. So much more than 180 degrees. And that's typical of positive curvature. So the rules of the geometry are changed depending whether you are in positive or negative curvature. This gives two beautiful results and so on. It's also very inspiring. And let us see some examples of artistic realizations which were inspired from curvature. So, where can that be? This is a picture is taken from a science museum in Dublin. And if you go there, be sure to visit the Hyperbolic Coral Reef Museum. It's not guaranteed that you will meet the lady who is here enjoying in the museum, but you will see these beautiful shapes which look like it's coral, but it's knitting made with a simple rule, negative curvature, constant negative curvature, the contrary of a sphere if you want. It looks like it's imitation of real life, but it's made from mathematical rule. And if we draw a triangle on this and measure the sum of the angles, it will be less than 180 degrees, and we can understand very well the geometry on this. It is also negative curvature, constant negative curvature here in this pseudosphere, which was exhibited on display a few years ago in the exhibition at the Fondation Cartier for Contemporary Art in Paris. And it is still constant negative curvature, which is the geometry of each of these units, is this kind of accordion, which represents the solution of some problem of mathematical physics. Now look, this look like such different objects, but if you take a piece of them, they will all look the same, constant negative curvature. And this is enough to determine it completely. We see on this example what I was explaining. Mathematics is about ordering, and see that sometimes the same equation is underlying several very different objects. So maybe it can be inspiring, but also it is not just something that you say once and which becomes the eternal truth. As in all of science, people will use it to develop it and to build on this more and more, and it will be more and more complex. And the work of Riemann was expanded and developed by people after him. Like this gentleman, Gregorio Ricci, who was an Italian geometer from the beginning of the 20th century. He developed this notion into what is now called the Ricci curvature, which tells you in which are the directions in which the curvature can be positive or negative in a sense. And it then left the field of pure mathematics when Einstein discovered, through conversations with his mathematical friend Boltzmann, mathematician friend, that the Ricci curvature was the key tool for expressing the theory of general relativity. Like this R here can stand for either Ricci or Riemann, but that's the thing that they developed. And you see, at first it's just for mathematical curiosity, and then one day, by accident, somebody discovers it's at the basis of the representation of space and time. And then, wait, more time, and gosh, it arrives in your car. In the GPS, there is a problem about some measurement about space and time. And it has to be done using information that grows at enormous speed, satellites and so forth. So you need to use the general relativity. So for this, you need to use the curvature, the Ricci curvature. For this, you need to use the Riemann curvature. So in the GPS, there is a little bit of Einstein and Riemann and many other engineers that have worked on it. Yes, if you open it, you will see the remains and so on. And it's the same very, very often. See, it took like 150 years before there was the idea in the brain of the mathematician and the moment where it is in the technology of daily life. Very often, this is the case. Now, Riemann was also very much excited about understanding some of the geometric patterns of the fluids, like, for instance, so-called singularities. If you look at fluids or light and so on, it can be this kind of cusp in your cup. It can be these lines of discontinuity of physical parameters when you have a supersonic plane called shock waves. Can be also the shock waves which are around the Kalashnikov. Whatever. This is not a very pleasant image, but look at the beautiful shapes here and here in the physical parameter. And Riemann wanted to understand this and develop the first mathematical theory about this. In fact, Riemann was interested in everything. And if you look the list of concepts which are named after Riemann, you just become very dizzy. Wow, is this possible? All the more that this guy was dead when he was my age, you know. This makes, this makes Riemann a very special romantic figure, you know, somebody who understands everything before in his short life and so on. Actually, once I met a very famous rock singer who told me that from time to time she goes meditating on the grave of Riemann for the inspiration, you know. Showing that sometimes the life of great scientists can be an inspiration for the artists. Because it's all about imagination, you know. I like that, and I too like graves, you see. This is Ludwig Boltzmann, one of my heroes. He died in 1906. Well, he committed suicide. Let's not talk about this. Anyway, 2006, 100 years later, I was invited as one of the main specialists in the world of his equation. I was invited to a big conference celebrating him in Vienna. I knew he was buried there. I knew it was famous. I knew that there was the famous entropy formula on the grave. It's a formula which expresses the fact that the discrepancy between our macroscopic world and the microscopic nature of matter with the atoms and molecules, the discrepancy between these two scales lead to a wealth of phenomena related to what is called the disorder of a situation of a gas, the entropy, which tells you whether it is easy or difficult to reconstruct the state of some gas, for instance, which you observe. I knew this. I had worked on his equation for more than 10 years, so it was natural that I visit him. You know, he was like family. So I arrive in the cemetery, and I see that the cemetery is huge. And I know there are these famous people. They are not just Boltzmann. There are famous musicians and so on. And I am desperate. How will I find the guy? And then there were some tourists around. So I asked them, do you know if there is a map of the cemetery where I can find the people? No map. Who are you looking for? Boltzmann. Aha, he answers the guy. Aha, S is K log W. That was the answer, the entropy formula. You see here, I like to say that this formula certainly is more important than the most famous formulas that we know, that like Einstein's equation, E is mc squared or so on. Because this is not just about special relations on microscopic quantum mechanics and so on. It is something that we encounter every day of our life, the statistical nature of the world. And in this anecdote, it was like if that formula, whose power I could appreciate, was transformed into a kind of password between people in the know in a cemetery. What did we know, both the guy and I, about then the nature of Boltzmann's discovery and the entropy? Well, Boltzmann and Maxwell, around 1865, 1870, they developed the idea according to which a gas is made of many, many very, very tiny particles with crazy velocity, crazy speed. This was very daring. Rest a little bit and think about the air around us. It's very quiet, right? Now imagine that in every portion of this air, there are billions of particles moving in all directions with crazy speed, bumping into you at each single second of your life, billions of them, and so on. No, don't try to do the particle. Maybe it's just a trick for establishing contact with the neighbor. Okay. Now, here is what the view. Let's take this model with many particles, and these are the velocities. So, from time to time, they bump into each other, and then the velocities are changed. Like a huge billiard game. How are we going to model this, and what are we going to learn mathematically from this? This was the challenge of Boltzmann and the others. And they understood that it was just impossible to look at the positions of all the particles and their velocities. So instead, they look at the statistics of the particles, of their velocities. This is Maxwell, by the way. And they focus on this curve rather than on the particles individually. Now it becomes statistics. And they knew they could take advantage, if it is statistics, of the large numbers. You know, if you want to handle complicated things, one thing, then another, then a third, then still a fourth, if you have many, many problems to deal with, it becomes a burden if you have more and more problems. But if you think statistically, the more is better. Like if I take a coin and I send it up in the air and see whether it's head or tails, it's impossible to predict. But if I do this 1,000,000 times, I know that roughly speaking, 500,000 times it will be head, 500,000 times it will be tail. So when you think statistically, large numbers are an advantage. And the problem of large numbers starts around 1700 with Jacques Bernoulli in Switzerland. Around 1730, Abraham de Moivre makes this extraordinarily important discovery. The Gaussian law, it's this kind of bell-shaped curve, equation like this, which he understands arises in the fluctuations of this problem of head or tails. Of course, if you send the coin, roughly half of the time it will be head, half of the time it will be tails, but there is some error. Is it a large error or a small error? Well, very often it will be a small error and sometimes a large error. And the statistics are given by this curve. Very often it will be a small error, but a few times it will be a large error, and this is the tails of the distribution. And this profile is typical. De Moivre can be claimed both by the French and the English. That's an advantage. He was a French seeking refuge from, religious persecution, because he was a Huguenot, as it was said. He was Protestant. let's skip Buffon for this time. We'll do it another time maybe. In 1810, Laplace proves that De Moivre's intuition is right, but also that it applies to all random problems, not just the problem of the coin tossing, but many problems in which you have a lot of experiments. For instance, if you do a pole, the error will be like given by a Gaussian. Or if you measure the fluctuations of the ocean, it will be like Gaussian, and so on and so forth. This was also exported to social sciences by Ketele in the middle of the 19th century. And Galton, who studied many, biological beings and so on, and human populations statistically, also marveled on the role of this Gaussian curve. I know of scarcely anything, he says, so apt to impress the imagination as the wonderful form of cosmic order expressed by the law of... Yes, cosmic order, thank you. Good. Cheers. The law of frequency of error, the law would have been personified by the Greeks and deified if they had known of it. It reigns with serenity and in complete self-effacement amidst the wildest confusion. It is the supreme law of unreason. That's well said. Back to Boltzmann. This is young Boltzmann. Between young Boltzmann and old Boltzmann, there is the arrow of time, and it's related to the entropy. The law that entropy increases, disorder increases, and so forth. So he was working on fundamental problems. And Boltzmann has this formula which tells about the disorder. The more that the state of a system will be fuzzy, the more it will be distributed, the more it will be, the entropy will be high, a lot of disorder. And he gives a formula for computing the disorder of a distribution of particles. And Boltzmann shows that you can study the entropy, the disorder of a gas. And he proves that this disorder is always increasing, and that this governs the behavior of a gas. Let us give an example. Suppose you take a big box and you put particles in one half of the box, and this is the void, okay? What will happen if you let the gas free to do whatever it wants? Well, we know particles will go all around the box. And we like to think that void sucks the particles in. However, Boltzmann tells us, the important thing is that the gas wants to have a higher disorder, higher entropy, and that's why it will spread all around, because it's more disordered. So he replaces the idea of a force by the idea of the rule of statistics. Here is an analogy. Imagine you have children coming out of a class. At the beginning, maybe they are near the door of the classroom, and this is where they can enjoy and so on during the free time, but pause between the two classes. And after a few minutes, they will be just all around, spread all around. Not because they like to go in places which are void, but rather because they all do things which are unrelated to each other. Two guys going to fight in this way, other being going to play that way, etc. So they are acting like particles which are chaotic and act as if they are all independent of each other, almost. Boltzmann was using these beautiful objects. Yes. Partial differential equations to make his claim and to prove his contributions. People like me are specialized in understanding these things, or part of them, and understanding how the solutions of these equations behave. Each of them represents a physical, natural phenomenon. For instance, that one is the Boltzmann equation, which tells you about the evolution, statistical evolution of a gas. That one is the Vlasov equation, which tells you, for instance, about the evolution of a galaxy, statistical evolution of the stars in a galaxy. This is the Schrödinger equation, the basis of quantum mechanics. This is the Euler equation, the simplest model for fluid mechanics. These are the compressible Navier-Stokes equations of fundamental importance. Each day they are solved on big computers all around the world to predict the weather that there will be tomorrow or 1 week from now and so on. They're also used enormously in the Hollywood industry for movies, for special effects, because you know it's much more efficient to use mathematical equations to reproduce special effects with water than to actually do the special effects with some water and so forth, etc. So all these equations have meaning, and you can write a whole book on any of them. Boltzmann was using this one to predict the behavior of the gas. It's like one molecule of gas, you cannot predict what it will do. But all the molecules together, statistically, because there are so many, you can predict with great accuracy what will be the evolution of the statistics. To take an analogy, it's impossible to predict if you look at an individual, you cannot predict when he will have babies, when she will leave the country or whatever. But if you look at the whole population, you can predict with very good accuracy over the years. If you know the natality rate, the death rate, the immigration rate, you can predict the evolution of the demographics of the whole country. It's the same with the molecules. Boltzmann discovered that this entropy goes up, and he showed how you compute the increase of entropy. There is some nasty formula that is there. And you can ask many questions when you understand this. For instance, what will the gas eventually do in the long run if I leave the gas alone in a box? Maybe there is some preferred state of the gas that we like. Maybe it's the most disordered of all states. So let's go for the maximum entropy and see what is the preferred distribution of the gas. And what we find, again it comes. The supreme law of unreason that Galton was speaking of, the law of errors. It is the equilibrium distribution of velocities in a gas. Around us, if you pick up a molecule, statistics of molecules around us, the velocity distributions will be Gaussian. And this is not only a mathematical theorem, but you can check this with the measurements extremely precisely. So this is the kind of thing that I worked on for a long time. Study about the increase of entropy. I worked on the conjecture by some Italian researcher about the rate at which the entropy increases and so forth. Many works I did with the Italian collaborators on the theme, how fast does the entropy increase, and so on. The Boltzmann equation nowadays is used for many things. Let me skip a lot of this, but just mention that the theories of Boltzmann were inspiration for many people, including Einstein and Smoluchowski in their theory of Brownian motion, or Claude Shannon in his theory of communication, which we use all the time when we send messages and so forth. And also it is used by engineers, for instance, to understand how the gas flows in a motor, in an engine of some car, and so forth. So once again, a huge gap, time gap, between the time it was invented and the time it was applied in our daily life, like more than 100 years. Sometimes, however, there are situations in which the application comes very near the invention, or sometimes the invention is motivated by the application. Wow. It's very apparent in the work of Leonid Kantorovich, another of my heroes. So Kantorovich was a Russian scientist. He worked on many problems from very pure to very applied, like atomic bomb or taxi fare. He was one of the pioneers of numeric approximation. He was a very, very clever man and very dedicated, always seeking the public interest and never his own. His masterpiece, his work in 39 and he's improved in 59, is the best uses of economic resources, a theory of planification which earned him the Nobel Prize in 1975 in economics. Kantorowicz is one of the heroes of a very weird novel which I warmly recommend, called Red Plenty by Francis Pufford, studying the rise and fall of the Soviet economy from the point of view of the mathematical idea, which is planification. Some of the heroes are imaginary, some are real ones. So you see Kantorowicz in here, you see Khrushchev and so on. And very well explain how in the old days, in the 50s, some very serious economists thought that the Soviet economy would become the first in the world because it was the only one that could achieve massive planification, which presumably can give better result as a whole. And how it collapsed partly because if you want to planify, it's not just the mathematics, it's also the men and women who are doing the economy, and they will not act like the plan hopes they will do spontaneously. Kantorowicz's life was completely changed, transformed by this, plywood. Yeah, plywood is not very sexy, but it's an invention of the father of Nobel. You put various kinds of wood together and you press them, so there is hard and soft wood, whatever. And there was this plant of plywood that needed to improve the results for the next plan, whatever. And they had the idea to ask advice from Kantorowicz. He was very young, but already recognized as a super mathematician. He had his professor position at age 22, you know, he was a very gifted guy. And he told him, like, Professor Kantorowicz, we have this problem, softwood, hardwood, some comes from this forest, some from that forest. We have a machine like this that can handle so much of this and that machine, this other machine. So there are so many possibilities. How should we organize the production to make it as efficient as possible? And Kantorowicz had no idea. But he thought about it and understood that by putting the problem in abstract formulation, he could make an impact. And that was the birth of the mathematical theory of linear programming. The basic idea of linear programming is simple. If in a problem which has several unknowns, in this case 2 unknowns, you can put all the constraints in the form of linear inequalities, like the admissible solutions of parameters have to be on one side of this line and that other line. Line is for linear constraint. Then in the end, the admissible solutions are part of a polytope, as they say, and one of these extremal points is the best. If it's just 3 equations, you can solve it by hand. I remember I had exercises like that in high school and was finding this so amusing. But now, in real applications, there can be hundreds of lines, hundreds of variables. It can be thousands, it can be hundreds of thousands in real applications. How do you do? Well, you need a mathematical theory for that. And that's what Kantorowicz developed. Kantorowicz found tools to solve the problem and also realized that it made it possible with these tools to solve an old problem set by Gaspard Monge at the end of the 18th century, called the optimal allocation problem. It's an economics problem too. Imagine you have something which is produced at locations x1, x2, x3, x4, and you want to send it to some sites where it will be sold, for instance, or transformed, y1, y2, y3, y4. How would you make the pairing between start point and final point in such a way that the total transport cost is minimized? This can be anything. Maybe here you extract things from the ground, here you transform it, whatever. But should you send this here and this here, or this here and this there? It doesn't cost the same for the shipping. And Kantorowicz, for instance, proved that you can transform this theorem into this problem into another problem, which would be like, imagine there is some guy who offers to do the transport by himself. And he says, okay, I will buy the good from you at this location and sell it back to you at the final locations. And we'll just discuss about finding the good selling price and the good buying price. And these two prices will be set in such a way that the difference of prices between start point and final point is never more than the actual transport cost. So that I'm just being honest. That's what the guy would say. Now, the mathematical theorem of Kantorovich says that if the guy does what is best for his profit, maximize the total profit, it will be equivalent for you to minimize the transport. It sounds like no big deal, this kind of theorem. But it was strictly forbidden in those days to tell about this in public. This seemed to be like a justification of capitalistic theory or whatever. It seemed to go against the Marxist-Leninist idea that price is determined by work and not by how much something is wanted. And it was strictly forbidden to say this in public. In fact, for developing a rational theory of economics, it is very clear that the likely fate of Kantorovich would have been death if it had not been for the fact that he was so important for other strategic problems like atomic bomb. Nowadays, linear programming is used for many kind of problems that arise in economics, as you can see in those examples which I took from a tutorial. And all these problems, can all be formulated in the same mathematical abstract way as an optimization problem and linear constraints. And you have many programs that can solve this. And of course, before you make the programs, the software, you have to understand how it works and which is a mathematical theory. And this is a very, very successful theory. It's used in particular to set up the prices of public transport or whatever. Okay, so far, so good, I hope. But we saw various theories, right? With common points and huge differences. We started with the Riemann geometry and the fat triangles, for instance, of positive curvature. Then we moved to the Boltzmann theory and the disorder and what it implies for the gas. And Kantorovich and his optimal economic theory and so forth. But now we remember that here this is about cocktails. And now we'll make a cocktail of these three theories. And that's exactly what happened to me around 2000, me and others. We discovered that these theories, even though they deal with different problems, different techniques, different applications, they could all be mixed together and be combined to get a new theory in each of these fields. It was not obtained by rational thinking, as most of the time it comes through chance and random encounters. You know, the life of a researcher is never like it's logical and you think and let's do this and this and this and see what happens. It's much more tricky. Here, let me borrow an image from a cool science blog. This is how some people think science goes, maybe. You ask a question, you think it's a challenge, you read, you think, and solution, Nobel Prize, whatever. In fact, anybody who has done science knows it's more like that. Wonder, accept challenge, read science. Somebody already did it. What the hell? Do math, some instrument breaks, whatever. Amazing results turn out to be crap. And then you start again. What the hell is going on? Thinking makes sense, no sense. Oh, that's good. Yeah, this makes sense. They figured this out 50 years ago. Now we are back and forth and so on. And after some time, wow, something comes out. It's quite like, that's the way it is, except that to this you have to add another extremely important ingredient. These are the encounters with the other researchers. So imagine this figure, but like many of these units tied together. And this is more like it. And sometimes you meet this guy, what the hell? Oh, this is, yes, oh, wow. In my case, 2 encounters were critical. First with Felix Otto, my German collaborator, met him in France and went to visit him in Santa Barbara in 1999. And then John Lott in Berkeley. This is the beautiful Berkeley campus. Politically speaking, this is the point of the place of all America, which is the most to the left. So, not bad, maybe. And it's always sunny. It's a great university and so on. This is the not so great math building. See how ugly, it's famous, the Evans Hall, so ugly. And when you are there, you discover it's not just ugly, it's not functional. Because people don't meet in this. It's like organization in layers. So if you are in this layer, you never meet the people of the layer below and so forth. It's a disaster, and there is no common space, so people don't meet. So you are here. I was invited as a visiting professor, visiting associate professor, sitting in my office, and I knew there were all these great mathematicians around, but not a chance to speak to them. What to do? My duties were very limited. There was no course I had to give, no administration. All I had to do was attend the lunch once a week and speak to people, and prepare a lecture during the whole semester, just one. Okay. And for this, I was paid 3 times my French salary. And in spite of this, I was not so happy because, sitting and what's going on? Until this guy arrives. He was invited by some institution nearby, uphill from there. And he talks, my name is Lott, I'm a geometer, I read your work with Felix Otto about entropy and transport, it's great, and we are going to use it to do this and this. What the hell is this guy talking about? And it was the start of collaboration. We collaborated for years, and we had a big hit with the start of some new theory. And what did we do? What did we develop? Building on previous work, let's call it the lazy gas experiment. It's a new point of view on the curvature. I will end with this. Mention that, of course, it is based also on the works of others. These are the people who really were in the development of this. My work with Felix Otto, Cordero is a French and Argentinian guy, Macan is a Canadian guy, Schmuckenschläger is a German guy, Sturm is a German guy, Lott is American, I am French, even though this is an Italian surname. Let me explain you now why the 3 stories I told you are all linked together and how we can understand this and see this. Let's ask whether the curvature is positive or negative. And let's try and ask it in a way that Boltzmann would understand if he was to come out of the grave. So, imagine there is this gas sitting in a certain configuration initially, and I ask the gas to change configuration. And this is the other configuration. Maybe there are some regions of low or high density for the gas. I don't let the gas do what it pleases. I ask the gas, this is your final destination. And the gas will obey, it has to. But the gas is lazy, so it will choose a trajectory which has the minimum energy, which costs the minimal energy, because it's a gas that wants to be as economic as possible. Now, all during this process, from initial configuration to final configuration, measure the entropy of the gas, the disorder, and plot the curve as a function of time. If the curve is always like this, concave, it means that the curvature has to be positive. And you see here a relation between geometry, that is positive curvature, economics, that is the most economical way to move, and statistics, because you are looking at the entropy. How do we understand this? Let me try to explain. This picture is like positive curvature, right? See the geodesics. First they separate and then they start again, a bit like you remember on the sphere. The lines were crossing once, then separating, and then crossing a second time. It's a bit like this. This picture is typical of positive curvature. If the curvature is positive, in between, the gas will be more spread then, because the separation between the trajectories is large. A gas which is spread is also a gas which is more disordered. Remember the gas spreading in the box, and its disorder increasing. So the disorder will typically be higher in the meantime than it is initially or finally in this experiment. And that's the result in this curve. So you see here how the three stories are related. And this is a new way to understand the curvature. It was actually one of the key ingredients in a thick book which I wrote after our works with Lot. Thick is something like 1,000 pages, you know, with big, nice, fat formulas. And this was also a way to solve some problems in geometry that nobody knew how to solve before, because the reasoning would go through statistics and so forth. If you are just geometer, if I may say, how would you imagine this? Why talk about the gas and the entropy? It looks crazy. But then by accident, some guys finds it. This is by accident. It's due a lot to chance encounters. And that's one reason why we know it's so important to have places for fostering unpredictable interaction. The institute which I run, which I have been running for 5 years now, it's an old institute, Institut Henri Poincaré. Yes, the guy in the being in the movie before the start was talking about that institute, right? It is devoted to inviting visitors from everywhere so that they can meet, so that they can interact, so that they can have new ideas. Who knows which it will be? We have different themes and so on, but we never impose any program to visitors. And chance encounters, most of the time, will give new ideas that nobody would have predicted. That's all. Thank you very much.